So the nice thing is we start our group projects here is that you have a team and the projects are dividable so that you can divide and conquer and split up the work and make more progress than working on it individually. And for project part A, we have the two major components and the associated testing with them. And that's the 32-bit full ALU and the barrel shifter. And today I just want to very briefly talk about a gotcha that is there for the design of both that you can lose a lot of time on if you weren't aware of what really the design requires. And let's walk through this together. So, the first important thing to note for the ALU, which otherwise looks exactly like your textbook 32-bit ALU, and also looks a lot already like the ALU you've already built, is that we have to design this circuitry for overflow detection. And one thing I've noticed that is a common misconception is that certainly when calculating overflow for unsigned quantities for things that are always positive, overflow is the same thing as a final carryout. Can we fit the result in 32 bits? If not, we've overflowed. Then we can look at the carryout bit to determine that. For our adder, for positive values, that's always the case. But for signed two's complement values of the type we are dealing with in MIPS, overflow is not the same thing as carryout. So when the assignment does ask you to build the overflow circuitry for project part A, it's not as simple as just taking that final carryout flag. Now I've hedged a little bit throughout the semester and I've mentioned that while it's conceptually important to be able to calculate overflow, in all practical purposes, in terms of the software that we are writing, where we're not really raising any exceptions, we're not doing anything when we detect an overflow. It's just a design exercise we need to go through, and it's really not super important in and of itself. So I just want to make sure you don't spend a lot of time over the next 2 weeks for this project stressing out about overflow. One way to think about of how we determine whether there's overflow or not is to figure out if the result is feasible given the signs of our input A and B. So if we assume again we're building our adder and we're adding two signed values, two complement values A and B. Well, the nice thing is there's only a few possibilities in terms of whether these are positive or negative results here, right? If we have, for example, we'll draw a quick little column here where we have A and we have B and we have our result F. If A is greater than or equal to 0 and B is greater than or equal to 0, for this result to be correct, we would expect F to also be greater than or equal to 0 when we add those two values together. Likewise for less than 0, right? If A is less than 0 and we're adding, A is a negative number and we're adding a negative number to it, for our result to be correct, we would want our result to also be a negative number, right? You're adding two negative numbers, the result should also be negative. So in terms of correctness, and there's the other permutations as well, right? If A is greater than or equal to 0 and B is less than 0, it's generally going to be okay. It's always going to be the correct result. We won't have a possibility of overflowing. And likewise, if A is less than 0 and B is greater than or equal to 0, we're in the same situation where it should not be an issue with regards to overflow. But for these first two conditions where we have two positive numbers and two negative numbers, there is a possibility, right, that the result of the addition would be something that can't be correctly stored in our 32-bit output. If we add two very large values, large positive values, we may wind up with a result that looks negative. That would be wrong. And if we have two large negative values and we add them together, we may wind up with a scenario where the result looks positive, and that would also be wrong. And so those would essentially be the two things we'd have to check for here. Are we adding two positive things and getting something negative, or are we adding two negative things and getting something positive? And the book doesn't really talk about how you do this. It'll present you with a version of this table, but doesn't really say, well, what does that mean in practice? The nice thing, though, about all of the things in this table, in which I kind of did a shorthand for at least greater than 0 and less than 0, can all be easily determined by just looking at that most significant bit, right? Our sign bit tells us that the value is greater than 0 or less than 0 for A, for B, and for F. So in fact, we can look at a single bit full adder. We'll use the plus symbol here, but we're referring to just now the single bit adder. And we can look at those inputs. That would be A31, B31. That's bit 31 of A and of B. Output, maybe now I called it F. You can call it F or you can call it S. It's fine. Output function 31. And then there is a little bit more, right? There is, from our perspective, there's that final C in, and call that C in 31. What you call this depends on how you label your wires. Maybe you just call it carry 31, that's fine. And then there is a final carry out as well. And there's only so many possibilities here, right? This is a 3 input, 2 output function for which we can just write down the truth table to determine whether or not overflow is happening. This is just for the most significant bit we have to do that. Let's try it here. So of our possibilities, we have A, B, and C in. And then we have our 2 outputs, and we'll call them F31 again and C out 31. And because we're interested in detecting overflow, this table's a little sideways, but it'll work for our purposes. Because we're also interested in detecting overflow, let us also add a column to this table saying, yes, overflow has been detected. That's just not gonna work. So let's add a column here for overflow. And we'll make do with the space that we've given ourselves here. And we can just write out the truth table. When is this going to be a scenario that we're worried about or not? It's a 3 input function. We don't have to overthink it. Just write out your possibilities. And give yourself enough room to do so. And we can do the math pretty quickly, I think, in our head for this, right? If we add 0, 0, 0, we get a value of 0, 0. And it may actually be even a little bit easier for us if it doesn't change the result, but if we write it in this order, where carry out is kind of our most significant bit here, and then F31 is the least significant bit. That'll make the math look a little bit easier, right? So we add that together, we get 0. We add 0, 0, and 1, we get 1. We add 0, 0, 0, 1, 0, we get 1. We add these, we get 2. We get 1, we get 2, we get 2 again, and then only when all inputs are 1 do we get both a function output of 1 as well as the carry out also being 1 here. Okay, so that's just our full adder truth table, and you can minimize the logic for it or just implement this directly in gates. Either way it works. So now we go back to that previous table, which for which of these scenarios is there going to be overflow? For which scenario did we add 2 values and we know just by looking at the output that the result is incorrect? And again, that would be when we've added 2 positive values and we got a negative value back out. Well, that would correspond to this line, right? We've added 2 positive values. And we're not guessing here. A31 is 0, B31 is 0. We've added 2 positive values. We've got a result in which F31 is 1. We've gotten a negative result back out. We have overflowed when that case has happened. And the other scenario would be we've added 2 negative values and we've gotten a result back out that is positive. So we didn't use the overflow column here. We ran a little bit out of space. But those are our 2 scenarios in which we've added something and we got a result that we know is wrong. And we can walk through the rest of these scenarios here, but they all are okay. We've added 2 positive values and the result is positive. We've added a positive and a negative. We can't say for certain, but it should just fit. So the result could be positive, it could be negative, but we should have enough bits to store all that information there. We've added 2 negative values and the result was a negative value. That also seems okay. So of those 8 possibilities of inputs to our 31st bit, our most significant bit of our full adder, of our ripple carry adder in our ALU, only 2 of them would correspond to overflow. We can do all sorts of logic minimization. You could take these inputs and try to minimize the number of gates. You can do K-maps and things like that. There's lots of ways you can try to minimize this function. The shortcut that will work just fine for our purposes today, that we don't have to overthink this issue, is that we can also detect that for those 2 situations for which overflow is 1, which is only just here and here, we can actually see that C in and C out are different. And those are the only two cases in which C in and C out are different. So in terms of what our actual logic needs to be to calculate overflow in this scenario, don't overthink it. It's literally overflow is going to be set as whatever you call those signals in your design. Um, but C out of 31, and when they're different, it's a problem. So it's XOR with C in of 31. And that's it. That's calculating overflow. You have now successfully calculated overflow. I'll make a separate quick video. This one's gone on long enough to talk about how to do your barrel shifter, but this is a standalone piece. When it comes time to implement overflow, if you want to design this from scratch yourself, you can. You can do a separate optimization of the function if you'd like to, but this breakdown works, and it just winds up being carry out XORed with our final carry in. Good luck on this.